All right, mathletes, so let's go ahead and talk about Chebyshev's theorem, also known as Chebyshev's inequality. Alrighty, so the big difference between Chebyshev's inequality and where we came from, which was the empirical rule, and again, if you want to watch that video, we have a link right here. So Chebyshev's inequality is for any data set, right? It doesn't have to be bell-shaped. And for the empirical rule, we discussed how it had to be bell-shaped, right? A normal distribution. So here we're talking about any data set. And what we're going to see is that the proportion of data that will be within k standard deviations is represented by this little formula here. And we're going to discuss what the heck does that mean, because that might be confusing. So let's break it down. Okay, so first of all, again, we don't have to have a normal distribution. We could have any distribution. And what this says is that when we go one standard deviation out from the mean, right? If we go, 2 standard deviations out, because this is Chebyshev's theorem, it tells us that at least 75% of our observations are going to fall within, right? 75% of our observations are going to fall within 2 standard deviations of the mean. All right, so that's what Chebyshev's theorem tells us. It also tells us if I go 3 standard deviations out, right, if I'm going in both directions, then at least 88.9% of the data will fall within these 3 standard deviations. All right, so let's put this into practice. Let's look at some examples. All right, follow me. All right, mathletes, so let's go ahead, let's look at this example. So we have a sample of n equals 50, so 50 observations, and it has a mean of 28 and a standard deviation of 3. Because it came from a sample, make sure to use the correct notation. Without knowing anything else about the sample, right? So we don't know if it's bell-shaped, we don't know anything about the sample really. What can be said about the number of observations that lie in the interval 22 to 34? All right, so here we go. What can be said about the number of observations that lie outside of the interval as well? So let's take a look. So according to this theorem, we know that if we're 2 standard deviations out, we know that 75% of the observations are going to lie between 2 values. But right now, we don't know if this is maybe 1 standard deviation, 2 standard deviations, 3 standard deviations, or some other amount of standard deviations away from the mean. So let's do a little bit of math first. So let's take that mean, that 28, and let's go ahead and add 1 standard deviation to it. So if we add 1 standard deviation to it, we're going to get 31 here. So notice our upper bound here was 34, so we're not there yet. So we're going to go ahead and add now 2 standard deviations. So let me maybe put that 2 in blue here, so we know that represents the number of standard deviations. And so order of operations tells us to multiply first, so we get 6. So 28 plus 6, that indeed gives us the 34. So notice we went 2 standard deviations to the right, and now let's do the same thing, and let's take that 28 and let's subtract now 1 standard deviation. And if we do that, we get 25, and we have not reached that lower limit yet. And so now let's go ahead and let's subtract 2 standard deviations. So maybe I should have done that in blue as well. All right, so now we're actually subtracting 6, right? Because we multiply first. 2 times 3 gives us that 6. So 28 minus 6 leaves us with 22. And now we've reached our lower limit of 22 here. All right, so notice we had to go 2 standard deviations out, right, in both directions. So what does Chebyshev's theorem tell us? Well, it tells us that because we went 2 standard deviations out, that 75% of the observations, right, of the data points of these observations lie between, in this case, these 2 numbers, right, 22 and 34. 22, and 34. But notice they didn't want a percentage, but that's what Chebyshev's theorem gives us, right? This inequality, that's what it presents us with. And I got to be careful, right? Let me put the words here that are very important. That at least, right? At least 75%, all right? So I got to be careful there. At least 75% of the data points lie between those two values, right? But what they wanted was what can be said about the number of observations, right? We haven't found that yet. So let's go ahead and let's take that 75%, which is 0.75 as decimal, and we're going to multiply it times however large our sample size was. In this case, they tell us our observations, we had 50. So we're going to multiply that by 50. All right. So let's go ahead and do that. Let's get our calculators. All right, and we're getting 37.5. 37.5. So what this means is that at least 37.5 of the observations are in the interval. But again, we can't have 37.5 observations. So what we're gonna do is we're gonna make sure to say that at least, I keep forgetting that word. So this tells us that at least 38, right, of observations lie between, at least 38 observations lie between our values, which were 22 and 34. And so some of you might be wondering or asking, wait, why did we use 38? Well, listen to what this tells us. It said at first we found that at least 37.5, at least, right? So the lowest number we can't go below is 37.5. But if we're talking about people, right? We can't have 37.5 people. And the reason we don't go to 37 is because the smallest number was 37.5, because it says at least. So it doesn't make sense to throw in a smaller number. So we're gonna go with the bigger number, which is 38. And so we say that at least 38, because that's the closest number to this. And remember, we want to include that, and we don't want to include the 37, because the smallest we could go is 37.5. And so we got to be very careful with that language here when we're looking at Chebyshev's theorem here. All right. And the same thing goes with this next question, right? What can be said about the number of observations that lie outside the interval? All right. So now we're going to talk about outside the interval. So we know that 3/4, right? 75% of the data lie between here. So for the second part of the question, what that tells us is that 25% of the data lie outside of this interval, 22 to 34. So 25%, so let's go ahead and do that. So to get that number, those numbers of observations, we're gonna do 0.25 times 50. All right, and so we're gonna do that in our calculator, and we're gonna get 12.5. And again, in this case, because we're talking about the outside, this is gonna be at most, right? Because it's the opposite. Chebyshev's theorem says at least 75% of the data is going to lie within. So the opposite is going to happen when I'm talking about the remaining, right? So at most, right? At most, 25% of the data is going to lie outside of this region. And so what we did is we multiplied 25%, right? Times 50, and we got 12.5. But if 12.5 is the most, right? It says at most. And again, that doesn't make sense to have 12.5 say people. So we can't go 13, because that would be over the 12.5, because it says at most 12.5. So since we're talking about whole numbers here, right? Numbers that we could actually count. We're gonna go with 12. So what we have to say is at most 12 observations lie outside of that range that they gave us. All right, folks. So there's our first example using this theorem. All right, so follow me. Let's look at another example here. All right, so this next example, let's take a look. The number of vehicles passing through a busy intersection between 8 a.m. and 10 a.m. was observed and recorded on every weekday morning of the last year. So the data set contains 251 numbers, right? So the sample mean was 725 and the sample standard deviation is 25. So in this question, they're going to change things up a little bit. They're going to say which interval contains about 88.9% of the observations. And if we go back to our definition of what Chebyshev's theorem tells us, we know that when it's talking about 88.9%, and I'll say at least, right? I should say at least 88.9% of the data observations. Well, we know what they're referring to is 3 standard deviations. All right. So here our K, right? We're looking at K equals 3 because we're looking at 3 standard deviations. So let's change this where it says about, we're going to say at least right there. So go ahead and make that change. All righty. So let's go ahead and let's do this. First of all, we're going to take our mean, right? Our X bar, which happens to be 725. And then we're going to add, and it doesn't matter if you want to add or subtract first, right? We're going to add 3 standard deviations, right? So each standard deviation is 25. And I should have put that down below. Let me change that. So it should be K times our sample, standard deviation right there. So K we said was 3, and we're going to multiply that times 25 because that was our standard deviation for this sample. All right, so there we have it. So we end up with 725 plus 75. All right, and now we simply add, and we're gonna get our upper limit there. So 800. All right, and now we're gonna do the same thing to get the lower bound, right? So we're gonna take that 725 and we're gonna subtract 3 standard deviations. And we know each standard deviation again is 25. So we're gonna take, and think of it this way, right? You start at 725 and you're gonna take away 25 3 times, right? We're gonna do 3 standard deviations away. So if you start at 725, you go 1 to the left, then you end up at 700, then another one, 675, then another one, 650, right? And so just to make sure, so we're left with 650 there. And so this is gonna be our lower and upper bound right there. So we know that at least, right, 88.9% of the observations are going to fall between 650 and 800. All right, folks. So hopefully this gives you a better idea of how to utilize Chebyshev's theorem, and we'll see you in the next video. Peace.